Um, Good morning, everyone. Thank you very much for attending our session on Sunday morning. The name of our session is What You Need to Know to Design Effectively in 10 nanometer and beyond. And in fact, I think our session goes a little beyond that topic. It will cover a wide range of topics, including new technologies and devices, design and layout techniques, design automation, and reliability. It is my great pleasure to have 4 distinguished speakers providing their own unique perspectives on some very fundamental aspects of IC design, particularly in the newest and the most advanced technology nodes. They are not only the state of the arts, but they also offer the experts insights into the future direction in our industry. So now, first let me introduce our first speaker, Dr. Greg Yeric. He is a fellow at ARM. Greg received his BS, MS, and PhD in microelectronics right here in the great city of Austin, Texas. He began his career at Motorola's Advanced Products Development, Research and Development Lab in the area of process integration. Subsequently, working at Test Chip Technologies, HPL Technologies, and Synopsys in the areas of test structures and the yield analysis. For the last 11 years, he has been at ARM Research, where he is an ARM Fellow focusing on future manufacturing technologies and their integration with design. Outside ARM, he volunteers on the VSI Technology Symposium Technical Program Committee and also on the Microsystem Exploratory Council for the Microsystem Technology Office of DARPA. Please welcome the title of his presentation is IC Design After Moore's Law. Please welcome Dr. Greg Yeric.
Thank you so much. Thank you. And thanks for your invitation to come. And Colin as well. I think Colin initially contacted me, and he did mention it was on Sunday, but he didn't mention 8:30 on Sunday. I thought, wow, if I had known that, I probably would have come up with a church reason to not be here. But the parking was great. As an Austin native, it was really nice. So thanks to everyone else, too, for showing up on a Sunday morning. I'm really impressed that we have this many people. And speaking of church, I thought maybe a couple people would have been conflicted, like, you're going to miss church to see this talk about Moore's Law. So I had you covered. I thought I'd bring a picture of a church. I just took an extended vacation in Italy, so I have 1,200 pictures of churches. So I went through all of my pictures, and I thought, okay, what picture most embodies the life of an IC designer? And I came up with this one. Well, I've got a clicker here, don't I? It was working when we tried it earlier. There we go. All right, so I came up with this one. This is, I'm sorry about the yellow font, but that's a around 1393 fresco of the Last Judgment. And you can see all these, the judgments are the things, your sins, you have to go to hell for your sins. And as designers, you've got plenty of things. You only get noticed when things go wrong. But that is, to me, is what design is like as a technologist, right? I on purpose have not gone into circuit design. But I do recommend this. This city's a great town in Tuscany. If you ever get the chance to go to this San Gimignano, there's the church, founded in 1148, and it's all these frescoes of all the stories of the Bible and everything. It's a beautiful church. So today, though, we're gonna talk about technology, and as we mentioned, the title is what we're going to do after 10 nanometers, after Moore's Law. And I'm going to break the talk down into a few sections. So the first section is I'm going to talk briefly where I think we are in the technology of Moore's Law. And then there are 2 schools of thought about what to do in the future. One school of thought is we're going to find a way to keep doing what we do well, which is shrinking transistors. And then there's another school of thought that isn't going to be enough, that we're going to have to do some other things. And those are colloquially often known as more and more than more. I'm going to talk about both of these. And then the stuff that I work on a little more closely in our research is after this, what is really going to come along that's going to propel technology going forward long term. And there are a lot of technologies that we bin in a group called Beyond CMOS. So these are the sections of my talk. I'm going to take you through all these. And the idea of this talk is it's not really going to be a tutorial about specific technologies in depth. I'm going to do a broad landscape of all of these topics that I mentioned, and hopefully leave you with some good ideas for things to go explore in your careers. Give you some reference material. So occasionally I'll have a little mention up on the top right of the slide. Of course, these are available to you as well, so you can have those later. And that's a key point. All this is available, so I'm going to be clipping along at this landscape pace. You don't have to take notes of anything that's on the slides, just other thoughts. And then out into the long term, I talk a lot with students at universities, and it's been some dark days for hardware people, talking about the ends of Moore's law and what have you. And one of the messages I hope to leave you with is that's not necessarily the case. There's a lot of opportunity in hardware going forward. Okay, so in terms of where we are with Moore's law, that's first topic. I, interestingly enough, gave a talk here 6 years ago. So I have slides from 6 years ago to help you grade me on my prognostication about the future. And it turned out to be a pretty good format for looking at where we were that amount of time ago, and now we're looking forward another 6 years. Back in 2013, we were really worried about the fact that we couldn't pattern the features anymore. There was this thing called EUV that was never going to work. We had to go to double patterning, triple patterning, quadruple patterning. That was the topic of the day. So back when the best chip you could buy was 32 nanometers, we could see a real headache going for 10.7 in terms of all this multiple patterning. As it turns out, EUV did finally make it. And EUV for a limited amount in 7 nanometers and then also in 5 nanometers is actually coming to help this problem, right? We can get back to some single pattern layers, get the cost down, what have you. If you have $100 million per tool. So there, on the design side of things, EUV helps. From the fab perspective, it's an economic issue. You've got to build bigger fabs and put more wafers through there. If you don't know much about what's going on inside the actual tool, the reason it costs $100 million is there's a lot of science fiction in the tool. So the way you generate the light is you have 50,000 droplets a second that you're propelling through this vacuum, and the idea is you blast this tin droplet with a laser, and that creates the light. They couldn't get enough light out of that, so they figured out now we're going to have a second laser. The first laser just tips the sphere into a disk, and it turns out then the disk shape creates more light when it gets zapped by the second laser. So there's this 50,000 droplet a second dance between two lasers, and it creates all this light. The light has to bounce off a mirror because the wavelength is so low, it doesn't go through lenses. The mirrors, you see these black and white stripes, those are 7 nanometer layers of alternating materials that makes this Bragg reflector. So across this huge surface, we're making these layers to exacting tolerances that make anything like Hubble telescope mirrors child's play. This is really, really, really high tech. But it works. And for all that effort, we can put EUV into a fab and we can make the wafers only 20-something% more expensive than they were before. So there still is this cost problem, and that's one of the central themes to Moore's law is with this cost per transistor every 2 years or 1.5 or whatever the current thought is. That's the question. So EUV has helped stave off the apocalypse of cost, and so we're okay at 7 right now. Now, what are we actually making out of these things? The transistors. When we go back to 2013, we could see the FinFET coming. The FinFET was causing us all kinds of headaches as designers. We're looking forward. We're not going to be able to change the widths. How are we possibly going to design circuits if we can't change the widths? How are these things going to behave in mixed signal form? Are they really going to work well? It really looked pretty troubling back then. And as it turns out, FinFETs worked fine. And we have multiple generations of FinFETs. One of the things to keep in mind is how these fins are getting taller and taller. And what we have been doing is using the fact that each fin is taller to take fins out of the transistors. So what you see going to the right is what we call fin depopulation. So the same standard cell is using, instead of 4 fins, then 3, then 2, and hopefully 1 fin per device. And that actually has hidden a lot of the problems with cost, shrinking the pitches, because we're not actually shrinking the pitches as fast as Moore's law would dictate, because we're taking advantage of the fact that the actual height of the cells is getting smaller by fin depopulation. So that obviously can't go on forever. 4, 3, 2, 1, there's no 0 fin device unless you're really into low power. But that has been that's been a Moore's law there that's been kind of hidden from view, and that's run out. So that's the summary. You'll get the summary in the slides. So where are we now? Everything's great at 7 nanometers. 5 nanometers looks okay. No need to worry. We're fine right now. So Moore's law N might be a misnomer. Now, what I want to get into now is how things look going forward past 5. So that topic we're going to call more. What are we going to do that's similar to what we've been doing, shrinking pitches and what have you. And if we go again back to my 2013 presentation, what we saw out in the future beyond something, EUV is it was so late that it has a limited amount of time that it can provide single patterning costs. There was an idea that this technology called directed self-assembly would help us. And that's using polymer lengths of polymer chains to create pitch features. And there's a lot of investment in this. All the big names, Intel, this paper I think might be from Intel, all the big names put a lot of money into this, and it didn't work. It just was too defective, couldn't inspect the features well. So DSA has quietly gone silent, a lot of the work on DSA. And then the other thing that is on a slide that we thought would be a dream that has not materialized is direct write E-beam. So there's an idea that you'd have E-beam. Of course, we can use E-beam one beam. We can make very accurate features very slowly. It's not good for high volume manufacturing. But the idea is we're going to do a lot of beams. And so there was a tool called Rebel that KLA tried to put out, and it didn't work. It didn't meet the specs. There are a few other tools that may meet specs, but for the moment, it doesn't look like this direct write E-beam is going to make it. So then the question is, what do we have going forward? Because EUV clearly is going to we're going to have to start double patterning with EUV, and that is a really bad cost situation. So between then and now, 6 years ago, there are 2 things that have popped up on the radar. One is a new version of EUV, and then the other one is a thing called nanoimprint. Now, nanoimprint, I'm proud to say, is from Austin, Texas. Has a lot of origins from the University of Texas in the chemistry department. And it literally is taking a 3-dimensional mold and pressing it into the photoresist, and miraculously hooking that mold back up without any defects, and doing it so fast on the wafer that it's affordable. It's again kind of science fiction that this could even work. They've been working on it for years and years and years. Canon ended up buying this technology, so you can buy this tool from Canon. It can make these kinds of these are sub 5 nanometer, sub 7 nanometer type of features. It can do it. It is pretty defective still, but the rumor is that some memory companies are pulling this technology into actual production, and memory can tolerate a bit of defectivity because you can correct for defective bits. To get to logic, we'll see, but there's a roadmap. Canon's pretty bullish on it, and as a designer, you got to love this stuff, because we've lost all that layout is 65 nanometer layout that we shrunk to 7 nanometers and said, Canon, if you can print this, then we'll give you our seal of approval from ARM, right? Because all of the arbitrary two-dimensional features allow us to make really compact circuits, and we've lost that ability. In the current nodes, everything has to be just a straight line that you connect. And then on top of that, once you make a mold, you're just stamping that mold. There is not this variation across light intensity and focus that you have with steppers today. So there's a lot of variation that is not there in an imprint. So not sure if it's going to make it. It seems to be, it's much farther along than I ever thought it would get. And as a designer, I'm rooting for it. We'll see how it goes. Now, the big topic is, and no pun intended, is the next generation of EUV. You can see there's a person down there for scale. And high NA, numerical aperture, if you're not a photography person, just means a bigger mirror. You just have higher angles of light coming in to image onto your wafer. So bigger mirror, bigger machine. That's about all it is. However, it looks like it's getting on the roadmap for maybe about 5 years from now. I don't know if you can see this in this picture, but there's a faint white outline. That's the current EUV tool. The new generation of EUV is much bigger. The current, that white outline box, required fabs to make buildings with higher ceilings because the tool's so big. Now, 5 years later, we're going to say make even bigger buildings because the ones you have right now won't fit the new tool. It's a big monster of a tool. And the interesting thing is, everything I've shown you, that's the box that you see in the fab. What the fun stuff is down below that box. There is a laser down there that is more powerful than the lasers that were proposed by Ronald Reagan when he was going to shoot satellites out of the sky in the 1980s, right? These are really powerful lasers because of how inefficient it is to bounce it off all these mirrors and get to the wafer. So just the laser itself is gigantic and is another act of engineering prowess that you couldn't believe would ever work, and it took forever, years and years and years to get to work. All that being said, there's been 3 orders already placed for this 2024 tool. And remember I said the first version of EUV is $100 million? These orders are being placed for $250 million per tool. So that, when people ask me what's up with Moore's Law, I'm saying, well, you can get some smaller transistors, but there is some serious risk involved at this point. So all that being said, this $250 million gamble is just to hopefully have second generation EUV only be 50% more expensive than first generation EUV. So again, lots of effort into really not a great cost story. And this, by the way, this chamber I'm showing, that's from the subcontractor Zeiss. That's the machine, that's the chamber they use to test their big mirrors. And at the moment, Zeiss actually doesn't know what material they're going to use for the mirrors, but they've already received $1 billion check from ASML to go start working on it. So it's just high dollar gambles at this point to get beyond 5 nanometers. Okay, so that was patterning. Back in 2013, we could see the FinFET coming. I mentioned that. But after the FinFET, we knew we were still going to need some performance boosts. At the time, we thought that some high mobility channels would come along and give us an extra drive current. None of that's happened, and there's been a variety of reasons. A lot of it has to do with the practicality of putting something in a 5 nanometer channel. When you look at gallium arsenide or silicon germanium or what have you, trying to contact it at advanced pitches, it just doesn't work very well. So nothing really out there at the moment for something beyond silicon. What has really taken the forefront is the idea that we're going to go from a 3-dimensional fin to a 4-dimensional 360-degree confinement with a suspended wire. So that's a horizontal nanowire. And I'm showing some cross sections on the right. What actually looks like it's going to happen is something called a nano sheet, which is you just basically make the fin, you cut it out of alternating layers that you then can selectively etch out. So you leave these suspended bridges between your source and drain, and then you have this magical processing ability to put the gate oxide and the gate material all the way around the suspended wires. And that's actually working out pretty well. And so that's what we all fully expect to happen, is this gate all around nanowire, nanosheet type of technology. What you get out of that is, ironically, at this point, you scale the gate length. You're really interested in scaling the gate length, not because of Dennard scaling, that doesn't work anymore, just to make room for the gate contact, or for the source drain contact. The source drain contact is the limiting factor at this point. So we're all excited about scaling the gate length because we can make more room for the contact to the source and the drain. The one thing that might be interesting about this from a design perspective is we might, because of this nanosheet, we might have the ability to order up some changes in the width of the device, which we haven't had in many, many years. So we'll see how that goes. Nothing that I put out in 2013, carbon nanotubes I had, two-dimensional FETs, those are pushing out. Nothing's really looking like it's ready for prime time at this point. So it looks like we're stuck with this horizontal nanowire for the time being. What we might want to see is some improvement pretty quickly, because this nanowire is really probably a 1 or 2 node kind of solution. And currently, the thinking is that what we're going to do is take, this is an inverter, so you've got some nanowires that are making an NFET, some nanowires that are making a PFET, and since you can already make suspended nanowires, and I glossed over this on the previous slide, in order to compete with the drive current of a tall fin, you need to stack at least 2 or 3 nanowires on top of each other to get the drive current to match. So we already have the technology for stacking these N or P nanowires, and the idea is we'll figure out how to stack N on top of P, and that'll give us a Moore's Law node of shrink. This is called the CFET, complementary FET, where you're looking down on it, and you've got N and P just in your floor plan. This is kind of what it looks like from a cross-sectional view. This was an older paper that had kind of vertical nanosheets. It's really going to look more like the horizontal nanosheet that I showed on the earlier slide, but that's generally what you're looking at from a process standpoint. It's not going to be easy. But design standpoint, I mentioned 3, 2, 1 fins. What do you do after that? Well, you do kind of get to this half fin where you're putting N and P on top of one another, and you get a 1 node cell advantage, a 50% shrink. This is a reference paper I'm giving you where this is a bit cell shrink, right? So SRAM bit cell, you can stack N over P and you get this great bit cell shrink, which we all need. The problem is a lot of the processing doesn't exist yet to be able to stack all this stuff N on top of P. So it's going to be a lot of work, but that seems to be what's kind of coalescing on the roadmap. One thing that in this picture to point out is looks like in order to get the density we need, we actually have to start using buried power rails in the logic. DRAM has used buried power rails before, so that process technology exists, but this will be a big disruption to physical design in CMOS. Could be very beneficial, because getting power down through a bunch of lithography constraints is difficult at this point. So going to a buried power rail, you can make those big, deep power rails to drop the resistance to maybe something a little more acceptable, and then also have some less congestion. But pay attention to that, because that'll be, I think, fertile ground for some design innovation. I'm not convinced about this whole plan. When I look at the parasitics and the drive current that you can get out of these nanosheets, I question if we're going to get anything that's close to the current FinFET performance. We'll see. It's on the roadmap. People have plans, but it's going to be a big challenge to keep performance up on this path. This is just a picture summary of everything I just said. I actually have a blog on the ARM site that has this graph and a few other things about 3D. So just a picture summary. Went to the FinFET. We're going to go to the gate all-around horizontal nanosheet. Then we're going to stack N on top of P for CFET. That's a one trick, right? Just that one stack. So what do you do after that? Stack CFETs. That's the plan. No one knows how to do it yet, but it's not. I don't make this stuff up, right? I talk to people. And here's a roadmap that you can. This is freely available on the internet here. IC Knowledge, where you see after 5 nanometers, the pitch, according to this plan, there's no pitch shrinking, right? All those pitches have stopped getting smaller, and you're just stacking more transistors to get this effective density. And the quick summary is we're just doing what VNAND already does, right? Vertical NAND just stacks, what is it now, 96 transistors in a column? And so when you look at it from a simplistic perspective, you think, hey, we already know how to do this, but that's memory, right? Memory is a very regular layout. It's a low activity factor, doesn't worry about thermal problems like high activity logic. So it's not going to be nearly as simple as VNAND, and I'm not sure it's going to work, but a lot of people are going to be working hard on making this happen. And right now, it looks like the best possible option out of the ones that are available. This is also just a reference article that might be helpful for you to understand. There are these big cliffs. The reason we are resistant to getting to certain pitches is once you get to a certain number, you have to go to double patterning with EUV, or you have to go to high NA EUV, you have to go to quadruple patterning. So there's a reason why you resist getting to a certain number, and it actually might be preferable to keep your pitch and stack transistors from a cost perspective. So it doesn't make sense cost-wise, all other things being equal. You stack a bunch of transistors, that's process cost. But when the alternative is buying a $250 million EUV tool you have to double pattern with, then it might make sense that you go to the stacking routine. So I hid this last column of that table because this last one is really entertaining. This is the idea that at some point it just is going to make sense to actually go back to 14 nanometer pitches and really stack vertically. Again, I'm skeptical from a power perspective. Not sure this is going to be great, but if you want interesting things to do in design, think about the fact that there's people working on a roadmap where they're going to give you 7 stacks of N and P transistors, and you can say, okay, I'm going to make a bit cell, I'm going to make an AOI. It's going to be, if this comes to fruition, very entertaining from a circuit design perspective. How to optimize around all this, how to route through it, that kind of thing. So we're not doing the simple things, just shrinking pitches. We're getting into things that really are disruptive to design. So there is a lot of opportunity out there for those of us in the room here. Once again, not sure about this from a performance perspective, but from a cost perspective, a lot of people are banking on it. The one other thing about shrinking, the transistors get all of the press, but really what the majority of the problem is now is the interconnect. Over half of the delay in a path in modern CMOS, in critical paths for CPUs, which we know at ARM, over half of it's the wiring, not the transistors. It's the contact to the transistor, as I mentioned, the vias and the wires, the R's and the C's. That's the problem. So you can shrink the transistor as much as you want. You're not going to get a lot of benefit out of the smaller transistor like Denard said we were going to get. That's all gone. And there really is not any good story in the interconnect. There's obviously a fundamental limit in capacitance, in the permittivity of a vacuum. There are limits to resistances of materials. If you've noticed, Intel had a huge problem with 10 nanometer, getting 10 nanometer out the door. That involved a switch from copper to cobalt. And that was for some very modest improvement in resistance and some improvement in electromigration. Very modest, but there's no other options. So they jumped into cobalt, and I'm not picking on Intel. TSMC is or will have the same problems integrating cobalt. It's a difficult material. And then there's ruthenium after cobalt. So another tip I can give you is maybe you can go find some ruthenium mine futures to invest in, because ruthenium seems to be the big thing after cobalt. But there's really not a good story on the interconnect. And to give you an extreme example, here's a study we did with Stanford where Stanford does some good work in graphene, which has some very good resistance properties. So we told Stanford, look, give us your best guess as to what you can get out of graphene. We'll stick it in our parasitic extraction tools and see this 10 gigahertz ARM core pop out the door. Well, the end result is if you squint really hard between the blue and the green on that plot, you can see a slight improvement from graphene to copper. But everything else, all the other parasitics that are involved, capacitance-wise and what have you, there's just not a lot of easy options in the interconnect. So that's why this is a summary table of everything I've said. That's why in this table, I'm not very optimistic about performance all the way down the rest of the nodes. There's just not a lot of good stories out there. But hopefully, so this is your reference material to take with you. Hopefully now, EUV, GAA, the gate all around, CFET, high NA EUV, All this stuff should be something you can refer to in the talk. The one asterisk I'm going to get to in a second, MRAM. So all that being said, maybe or maybe not 2 nanometers is going to be worth it. We'll see. So the question then at the beginning of the title talk is Moore's Law really dead? Well, if you can run 120,000 wafers a month in a mega fab and can afford some of these EUV tools, there is a path, if this stacking stuff works, to say that the transistor cost is going to go for a while. It's going to continue to shrink for a while. Rock's law is commonly referred to as Moore's second law, but there's a person named Rock who also worked at Intel who had this law that the cost of the fab is going to go up exponentially just as the cost of the transistor is going down. And he turned out to be just as good about predicting the future as Moore. And at some point, you're going to have country-level investments to get this stuff done. It's really not clear that an Intel or a TSMC or a Samsung will have enough money to do this 1 nanometer fab. So that's the risk that's involved. And that's why you have to think Moore's Law, the concept is in troubled state. And of course, as designers, we all know, we assume from shrinking transistors that we're going to get power and performance improvements. That's all gone. All the Dennard scaling is just, there's nothing there. And from that perspective, then from a design perspective, it's pretty acceptable to say, look, Moore's Law is over, we've got to do something different. So this is a summary slide of everything I just told you, just for your reference, where we are. Not very good power performance scaling. There's a story to some transistor scaling with some stacking of transistors, blah, blah, blah. So this is just for your reference. You've got it in words. But the last line I want to underscore is the risk. So there is Moore's Law, the idea that the next node is going to be a little bit cheaper. But the real power of Moore's Law is the contract, the guarantee that if you wait 2 years and you give me money for the next node, your circuit's going to work better. And that contract that's the risky part now. So what I think of as the end of Moore's Law is what has happened now is people are seriously looking at getting off of that treadmill and looking at different ways of doing things. Because the risk to get to 3 nanometers or 2 nanometers is super high. And that's, to me, that's when Moore's Law isn't an automatic bet, then it's over. And that's where we are at the moment. So that gets me to the other topic, which is more than Moore. So if we're not happy with Moore's Law, what can we do that's outside of the transistor shrinking, getting circuits better paradigm? And that's all the stuff that can happen in Moore's Law, more than Moore. So I'm going to break it down into 3 pieces. There's things you can do technology-wise, there's things you can do circuit-wise, and there's things you can do at the system level. And I'm going to start with the circuit side because I'm not going to talk a lot about that because you're the experts. And you already know this happens. You already know, you're already doing things, right? For years and years and years, you've been doing write and read assist of SRAMs. You've been more intelligently dealing with variation to get some of the guard banding out of the circuit design. All that stuff you know. The only message that I want to leave you with is EOML means end of Moore's Law, is because this contract of Moore's Law is essentially over, you may have had some great ideas, say 5 years ago, and it was going to be a really complicated design problem, and it got vetoed because we were just going to go from 16 to 10 nanometers. It's going to be easier. It's now the point where you might want to revisit some of those crazy ideas in circuit design because the contract with Moore's Law is not necessarily the same level of guarantee that it was before. So what the end of Moore's Law really means is there's actually more opportunity, more power in the hands of the circuit designer than there was. So whatever you've been doing, keep doing it and thinking up the great ideas. So I'm not going to spend a lot of time on the circuit side. I'm going to give you one example from ARM research just to show you the level of craziness, perhaps. And that's in the area of timing guard banding. So again, this is stuff you guys are experts at that I don't need to talk to you about, but you guard band across noise, temperature margins, voltage margins, process margins, and we derate a whole bunch out of what is hypothetically possible from the technology. And I want to show you one example from voltage margining. So there was this crazy years-long research project at ARM where we made a digital oscilloscope, stuck it on ARM cores, did a lot of rigorous simulation to measurement matching so that we could then do genetic algorithms to predict what kind of input vectors were going to cause an extra 2 or 3 millivolts of voltage droop. So crazy amount of work, and it's the kind of stupid stuff that research will do with no reason other than it's interesting. And I lost my clicker again. There we go. Oh, there we go. So here it is. There's a paper I've given you reference. You know, is it just crazy to put that much effort and maybe even put this much of real estate onto a chip just to chase a few millivolts? Well, when there's no other performance improvement from the circuits, and you're going to be spending hundreds of $millions on a design at 5 nanometers, then yeah, this level of effort in circuit design is actually worth it. So I predict you'll see this not being just a research project, but you'll see this kind of thing showing up in products pretty soon, because these are the type of stuff we're left doing now to eke some performance out of the modern nodes. Okay, on the system side, this is a wide topic. I'm going to try and cover a few key pieces. One of the main pieces is the idea that we all know because of the poor Dennard scaling, we're power limited on putting enough transistors onto the chips as we're entitled to. And of course, we got into this era where we put multiple cores on a chip. Great news for ARM. We made cores, and people are putting more cores on chips. So it was a fun time for a while. But the general trend is that we can't afford to turn on all the transistors that we're given from Moore's Law. We have to get good at getting things out, useful work out of the transistors with lower activation, meaning we're not going to turn them all at once. We're going to do a few key pieces that we need to do calculation-wise and keep the rest of the stuff off. And a broad term for that dynamic that I just mentioned is accelerators. Accelerators we're not just going to have one big CPU that does everything generically. We're going to add specific circuits that do key things well and then manage that on a system level. There's a ton of work in this area. The idea of accelerators is not new. Multi-core is an accelerator. Big, little is something that ARM did. Big cores, little cores. GPUs, that's an accelerator, right? It's a dedicated set of transistors that are really good at the graphics. And now, of course, we're getting into tensor processors. So there's a lot of stuff that's already out there in accelerator land, but it's a huge hot topic. In this particular paper that I have referenced, I did for a reason, because there's a really interesting job of looking at, by the domain that you're concerned about, what are some of the accelerators that you can look into, and then they did a fairly formal partitioning of the options per accelerator in terms of design space. And basically come to the conclusion that let's not get too excited. We're not going to ever put 100 accelerators onto a chip, because that ends up not making sense. You've got some interesting pieces of that here this year. I see session 4 has stuff on accelerators, so if you're interested in this topic, circle that in your program. What we're seeing in ARM land is a ton of exuberance on this topic per accelerator. But if you look at actually making a system, some SoC, and you're talking about putting 3-4 different accelerators on there, what you find is trying to integrate multiple accelerators onto a die, they start to conflict with each other. So putting a second accelerator dilutes the power of the first accelerator if they're having to use common security protocols, memory protocols, what have you. So when you might have something that does a really good job at that thing you're doing. You're a graph processor, and you've got a graph processor accelerator. Great. Are you doing graph processing 100% of the time in your system? Are you doing any other kind of accelerators that are going to conflict with it? So you start with this exuberance, and when you actually come out with a product, it's better, but it's not as beautiful as you thought it was going to be when you actually look at the full system level. I noticed there's one panel that looks like it might get into this topic. So this will be interesting. This machine learning panel where we'll talk about this particular question. But independent of the domain that you're interested in and the type of calculations you're worried about, there is one thing that all domains and accelerators can agree on, and that is that the memory is too slow. Memory is too slow. It's getting slower. The dynamic is that we have been making lots of great progress on the frequency of calculations, but the memory latency has not been scaling. It's been going on for decades, and it continues to be a big problem. And the ironic thing is, the worse the memory is, the worse we use it. So as we get these big latencies, we have to do more crazy things at the system level, like prefetching, speculation, grabbing bigger chunks of memory when we only need a byte. So we actually compound the problem. As the memory gets worse, we use it less perfectly. So it's a compounding problem, and it's a very specific near-term trend that is continuing. So this is just an example of some calculations of anticipated core frequency versus anticipated DRAM standards in frequency. And we're projecting that we're going to continue to have these big problems just feeding data into these big multi-core chips from just a memory standpoint. And it's not just the speed, the power story is just as crazy. So we can do calculations efficiently because Moore's law and Dennard scaling have been going pretty well. And that has not been the case for the memory side of things. So you can calculate so much more efficiently than you can move data around. And that has a dynamic that's really flipped just in the last decade or so. So now and going forward, moving data is more important than calculating with the data. That's the dynamic. And so there's a lot of opportunity at the system level to do things that are going to improve that. One of the big topics is what we call processing in or near memory, PINM. And that has to do with this, how inefficiently we deal with data. So we have these level of caches. We speculate that data's in a cache somewhere. We do stupid things like ask the memory if it has the data we want. Stupid question. Or can you move the data around in your memory, or can you order some things differently? So there are opportunities to put intelligence into the memory levels to do some of these simple things. Rearrange data, query data, these kinds of things. So this is the topic of processing in or near memory. Lots of opportunity to really improve at the system level with some clever circuit design that's near the memory, not part of the CPU over on the left. And I've got you some good references for reading in these areas, as well as the fact that I found you've got plenty of that happening here at the conference this week. So there's session 15, looks like it's got some good stuff, and then 24, lots of great stuff. These speakers are top-notch in the field, so definitely go visit this session for this very fertile ground in areas you can contribute in the circuit level. One other reference, so this is compute in memory is another acronym for the same thing, CIM. This is a list of domain-specific things you can do with compute in memory. It's a good reference paper to look through for some of the options that you have. Okay, so the last part is on the technology side, which is actually what I do. So I'll spend some time talking about technology options in More Than More. So this is, what do we have in the technology widget bag that is not shrinking transistors? And I'm cheating in a sense here, because my first topic, actually Gordon Moore put in his paper. So he has this quote: "It may prove to be more economical to build systems which are separately packaged and interconnected." So he's in 1965 predicting 3D IC, right? 3D IC is a huge area of opportunity for us to do things more efficiently. And the early adoption examples are very clear about this. So you look at the big GPUs. They went from trying to access DRAM on a board in a two-dimensional space to this high bandwidth memory that's stacked and then accessed through high density buses. And they're getting not the 5%, 10% kind of improvement in power efficiency, 300%, right? Just use 2.5D, I get 300% improvement in power efficiency. So the 3D's here, it's for real, it's here to stay, and we've got real products that are driving it. But it's not just the performance angle. The bigger chips, I showed the 96 core, 100 and whatever core, the big chips, because you're trying to put so many cores on these chips, they get big, and because the yield is a function exponentially of the area of the chip, it actually makes economic sense to break a big chip into smaller pieces. You actually make money doing that. And cost-effective 3D or 2.5D lets you do that. So here's an example from AMD where they took a 32-core chip, broke it up into 4 pieces, and they saved 41% in their cost. So pretty straightforward. If you can save cost, you can bet people can start doing this more and more. From this same paper, interesting little plot there where they're showing that over their history, they're only getting 40% of their benefit from Moore's law, and everything else is fancy design stuff that they do. And 3D's the next big step for them. Now, huge caveat though, in order to get that full yield benefit and the cost benefit, the pieces that you break things up into need to be fully testable, and you need to know that they're known good die. That's a huge asterisk, and that's, again, a big opportunity in this space when you talk about other pieces of chips, is how to make things that are testable. Now, another paper that came out at the same conference, IDM 2 years ago, Global Foundries said, look, you've got 41% improvement. We even got better than that. We got 63% cost improvement with 3D. What they did, pretty smart, they just took the memories out of a system, made one layer that was all memory. Memory layers were repairable. So that basically they took a big chip that was yielding some number, and then they put it in 2 layers where one layer yields 100%, and then the rest of it is logic. So if you have a defect in a big SoC, one defect in the logic kills all your memories, right? So huge cost savings for these big chips. I mentioned early adopters, and I realized later as I was preparing this talk is one of your keynote speakers here actually was one of the people at Xilinx that did a lot of the early groundbreaking work in 2.5D. So he's not going to be talking about that now, but I wanted to cover myself in case I found him in the hallway and he said, hey Greg, I noticed you were talking about 3D and you didn't mention Xilinx. So you can ask him questions about the early days if you want. Okay, going forward, what's the next level of abstraction or functionality? And that is full chips that are stacked, which we call chiplets. And the chiplet era is here. So the next thing that AMD has done is to take the logic down to 7 nanometers, but keep all the I/O at 14. That makes tons of sense from many angles, right? I imagine many of you in this room deal with mixed signal. A lot of those devices are not happy about shrinking from 28 to 14 to 10. So why not just use them in the nodes where they're optimized, and then spend your cost just shrinking just on the logic. So that dynamic is here to stay. The key is how you do the communication between these chiplets. So AMD has a way that they've done, but there are no standards for the industry now. There's going to be a lot of room for improvement in terms of innovation for how you do I/O of chiplets. Physical standards, logical standards, all that kind of stuff. This is going to be a really, really active area. So if you're bored, and you're looking for something to do, and you're an I/O person, then I've got some good news for you. There's lots to do. And there's a session here at CICC, session 19, that's got some interesting looking papers in this area. So just as a summary, for chiplets, one of the really attractive things is instead of doing the design effort to shrink an entire SoC, let me just spend the 500 million kind of number just on my cores, and then I can reuse a lot of stuff that doesn't necessarily need to shrink anyway and save a lot of money. So cost is king, and this is, you can see the wave of chiplets coming just from economics. It's definitely going to happen. So this is somewhat of a reference slide as well. This is from IMEC, talking about the different advancements of 3D technology, basically from left to right, looking at increasing interconnect density. So what I've talked about now is things that are fairly granular. They don't really mean circuit design because the pin density is not high enough. But in development, there are things that we're going to use as circuit designers. And that's the exciting thing for us, right, in CICC land. Now, I already talked about the transistor stacking, so that's coming, and that'll be its own special fun. But the other stuff, there's actually one interesting exception to in development. There's actually a wafer-to-wafer technology that's coming online now. So all of you have this technology in your pocket right now, and I'm looking around the room, and my next bubble doesn't have a target, but I was expecting someone to have their phone out, and I could say, well, you have it in your hand instead of your pocket, but you're all paying attention. That's amazing. So anyway, we all have this. It's the camera chips in our phones. They're using wafer-to-wafer bonding for very high-density interconnect. The cost and functionality reason for the cameras is this, and they're not quite there yet, but to get to a per-pixel stack of sensor, memory, and logic. And that will give them a huge advantage. You're starting to see some products, like there's 1,000 frame per second camera, I think, on the new Apple phone. And a lot of it has to do with the fact that you can put memory right under the pixels of the sensors. Now, there are really impressive wafer stacking machines that have been built to do this, and the logic fabs are starting to buy these machines. So you can just see this wave coming over to logic soon. As TSMC's announced, I know GlobalFoundries has announced some stuff as well, roadmap-wise, right? You can't do it right now, but I would think in this next year, you're going to see some announcements along these lines in the logic fabs. We did some studies at ARM just looking at CPU paths, right? So if you can intelligently take a CPU and fold it into 2 tiers where you're getting rid of the long wires that are the delay problem, you can get really impressive performance improvements out of this wafer stacking technology. So I mentioned, I'm expecting 0 to 10% improvement in performance per node. Call it 5%, right? Nothing really exciting per Moore's Law node going forward, but you can get a really nice boost of, say, 20, 25% by shortening paths to 2 layers in a 3D sense. So in that regard, it's really exciting, and it's virtually free. The stacking step is nothing. It's just taking 2 wafers, you stack them together. It's not expensive like building a FinFET or buying an EUV tool or what have you. One asterisk is you need 2 mask sets, right? So that is a cost up front. But other than that, it's a really, really attractive technology. That was the logic paths. In the memory instances, it would make no sense at first to think that this black highlighted, that a transistor is going to be more efficient for a transistor and an SRAM to communicate all the way up through the stack of one wafer, through the stack of another wafer, and visit a transistor in a different tier. But it turns out that actually does make sense in these larger memory instances. So when you analyze the paths of these larger memory instances, you get the same kind of improvements, much more than 10% in terms of frequency by just stacking them in 2 tiers. And then at the system level, you've collapsed these memories into half their size, and routing around them is always a problem at the SoC level, and you've erased that barrier. Now, all that is very Pollyanna-ish in the sense that this would be wonderful if we could do this, but as many of you are probably spinning in your heads, there's no way you can do that right now, in the sense that we don't know how to deliver power, how to deal with thermal issues. There's a lot to be done in 3D land. This is just one paper we've done. In this area, look up Professor Lim, Sun-Kyu Lim. He's done a lot of the early work in understanding what needs to be done going forward in design land. And this is just a power delivery network example. So to summarize, it's a really interesting technology. I really feel pretty bullish about it. Putting the wafers together is the easy part. I talked to you a little bit about the design part. That's probably in the wheelhouse of most of you in the room. Really interesting things you can do to get really significant improvements. But then when you do this, you start to realize that the problems just keep percolating up higher and higher. So if I can give you twice as much memory, or it's this much faster, or I can give you 3-dimensional meshes of cores, it starts really getting into problems that percolate all the way up into the system level. So lots of great stuff to do in circuit land, but to really take advantage of it, there's a lot of communication that has to be done all the way up through the stack. And then none of this can happen right now because there's no EDA tools you can buy for 3D design at the moment. There's a lot of it is in development. There's a lot of great work in development. But if you look, every tool that you use in the existing design can't conceive of three-dimensional concepts. It has to be built for 3D from the ground up. There's not a lot of hacks you can do in that regard. So there's a lot of work still to do. Now, that was a discussion about plain CMOS CPUs. But the really exciting stuff is if you can put wafers together, they don't necessarily have to be the same type of wafer, right? You could put a CMOS underneath an RRAM, underneath carbon nanotubes. And what I'm discussing actually is this paper from Stanford, where in addition to heterogeneously stacking different things, they're using it in a machine learning architecture that specifically is designed to take advantage of the high-level interconnect density. And when you do this kind of ground-up innovation, you're not talking about 25% improvement in your metrics. He's talking about, Professor Mitra, 1,000 times improvement in his metrics for machine learning. So these kinds of big jumps, if you look at the technologies available and then re-architect what you're doing to take advantage of it, there are some big improvements out there. I have arguments with him about the 1000x, but it's more than 25%. It's closer to 1000x. So that's the punchline. Is there's a lot of opportunity for 3D. So this is just a printed summary for you to take home about what I just talked about. A lot of problems with technology innovation is who's going to get it started. And that's a lot of the questions I get in CPU land. And I just point and say, look, the image sensors are going to drive this. They already are. Now you have the big iron people, the NVIDIAs and AMDs are going to drive it. So the costs and everything are going to come down because it's saving the big people money. And then we get to take advantage of it. Lots of opportunities in circuit design. Tons of advantage to not only do CMOS better, but to think about what can I stack heterogeneously together that I never could before. Okay, so the next technology piece that's important more than more is all of the various potential new non-volatile memories that are coming out. So we have, for the last, whatever it's been, 30 years, one embedded memory. And it's a really horrible, stupid memory, right? This floating gate stuff is a really horrible memory, but it's the only one we have. It really looks horrible from a design standpoint. It's slow, power hungry. You got to do, high voltage wells, all kinds of weird problems. So what we're after with some of these newer memories is to get around some of these problems and get, for the first time ever, some ability to use them in modern CMOS nodes, logic-wise. And there's a wide variety, so I'm giving you kind of a reference table of the various technologies. But what I will say is all of these look like they're going to be better than NOR, but none of them are near perfect. What we want, of course, is a DRAM-sized cell that's as fast as an SRAM that lasts forever, right? If we had that, we'd really be in business. And none of these memories do that for us. I'm not a big fan of the resistive memories. The filaments are just too stochastic, and the reliability is too low. Right? You can't use that from a logic perspective. Though you can get it from TSMC now. You can get RRAM, I think, at 22 nanometers. It's a lot better looking than the flash type technologies for embedded. But from using it in logic, I just don't see it happening unless there's some really big fundamental improvements in the various technologies. Phase change memory, you've heard a lot of noise from Intel and Micron, but from a foundry perspective, it actually just got announced by ST. So you can buy phase change memory, embedded phase change at 28 nanometers. Pretty decent memory, too slow for logic, and a little bit too high power as well. But still, so much better in some regards than the flash that we would have otherwise. There is a not well-publicized initiative in a new kind of ferroelectric memory. The main driver here is out of Germany, GF in Germany, and then there's a German company called Ferroelectric Memory Corporation. It's a different kind of ferroelectric memory than you had in the 80s. It's better. It looks really interesting. It's just a little slow. It doesn't look like it's going to be fast enough for logic. And then the last one that you can get everywhere is ST-RAM. So you can get that Samsung, TSMC, Intel is announcing it, Global's had it for a while, so everybody's on the STT-MRAM bandwagon. And this is a layer stack of the resistor for MRAM. What you're seeing is the materials and then the layer thicknesses that are required to make this. So it is crazy. This is where we are now, right? In how bad the pursuit of Moore's law has been, that these fabs have agreed to do this, to even try it, right? And they did it, right? You can buy MRAM. So you put all these angstrom level, platinum, cobalt, iron, everything that's going to take a fab down from an impurity standpoint, stick it in a resistor, and you get a resistance difference of 2 between on and off, right? So again, as designers, it's not the best technology in the world. It's just what we have available. It is fast, so it's got a potential speed-wise, and it's got pretty good endurance. So there's hope for MRAM. You just have to be able to design with this factor of 2 difference. And the other thing I'll mention too is it's not that robust in addition to the resistance. So when you actually look at a memory instance of MRAM, it's not 1 or 2% ECC. It's 25, 30% ECC. It's a messy technology. But if you do it right, you do actually have a pretty good memory. The one thing you'll notice with all these technologies is none of these numbers are infinity, which is what we would like as a designer. We want infinite endurance, and then we can just use it and not worry about it. But what will be an interesting set of activities going forward is these new memories are going to come in at different nodes. They're going to have different levels of endurance. And the fun we're going to have in circuit design, the opportunity is for a given technology, a particular memory at a particular node, what can we do as circuit designers to get the most endurance possible? And then given that, where can we place it in the hierarchy of things that need endurance? So you need 10 to the 18th kind of numbers if you want to stick it in a logic transistor, but as you go higher in the cache level, there's some ideas that we're probably going to get an MRAM type of thing to work at the higher level caches. But this is going to require some serious circuit design work to get done. One example I'll show you, this is a paper that we're going to publish with Stanford at DAC. So this is a little pre-print thing. But the quick thing I wanted to point out is this is just a kind of an envelope function of the energy area curve for using an ML, a TPU kind of processor, using off-chip DRAM is the red curve, and then using a very idealized RRAM, which are the bluish curves. They look so much better than going off to DRAM, as you'd expect, in terms of area and energy. But that's not accounting for the fact that RRAM doesn't have very good endurance. So if you do the things you need to do to deal with the small endurance, then those curves don't look that great anymore. So for some of the larger instances, yes, but you really have to pay attention to this difference in how you deal with non-infinite endurance in these memories, and you will find that there are cases where they're not really that compelling, and cases where they are, but a fair amount of work to do to get to that point. So if you're interested in that topic, by the way, my coworker is going to be here later in the week. You can go bug moot it. He's doing a talk on puff design, but he did a lot of work on that DAC paper that's coming out. Okay, so MRAM looks like it might be the one that's getting the big momentum here. And the idea is on the CPU cache level that MRAM's pretty good, except the speed is not that level. MRAM can't get down into the 2 nanosecond range at the moment. And I just put this on as a good reference paper if you can get a hold of this short course. What you actually see with MRAM is it can be both those smaller red boxes are STT-MRAM. MRAM can be made to be fast, or it can be made to have high endurance, but not both at the same time. So you can order up an MRAM, perchance, if the founder will let you do that. You can order up MRAMs that are constructed to be one or either, but not both. And that's the problem, right? So you can have fast, but it's not very great endurance, or the other way around. So that's what this next generation of MRAM is hoping to improve upon. That's spin orbit torque, SOT. So spin orbit torque is in development in a couple of places. I'm showing a paper here on the lower right to show you that hardware is being made. So IMEC has made spin orbit torque memories at nanometer dimensions that have pretty encouraging numbers in the hardware. So it's looking pretty encouraging. The basic idea on the picture on the right is all you're doing is you're decoupling the read and write ports of the bit. So now you have a 3-terminal device instead of a 2-terminal. So it's a bigger bit you have to wire to, but then you get the benefit of speed and endurance. And I'm not going to talk about voltage contrast, which is the last one. That's the holy grail, actually, but it's too new. We don't really know if it's going to work or not. Maybe 6 years from now, we'll be talking about that when I come back. And the other thing, too, when you're looking at these F-squared numbers in this table, be very cautious about what you're doing, because people throw around these F-squared numbers without underscoring the fact that SRAM isn't scaling well from an F-squared perspective. So if you're comparing leading edge SRAM, it's not the same number of F-squares as 28 nanometer SRAM. You got to be careful with MRAM to SRAM to RRAM, F-squared, depending on the node. Just be aware of that. So MRAM does look compelling. The numbers on that previous slide, not that great, but MRAM does look compelling at compared to 2 nanometer SRAM on an F-squared basis. So all that, I went through that whole MRAM story so that this final table, this is my prognostication table. The one other thing in red that I hadn't talked about when I put this table up at the beginning of the talk is that the idea is that we're, from a Moore's law perspective, the idea is we're going to replace an SRAM bit cells with smaller MRAM, SOT MRAM bit cells, and that is going to be part of the transistor density story at 2 or below nanometer nodes. And it's looking like a reasonable idea. So that's the last term in that table that I wanted to make sure you knew before I left. That's just the memories. So looking at beyond memory caches, that's when the fun's going to be for circuit designers. So if we, as these memory technologies mature, if we can get the ability to put bits out arbitrarily instead of just big caches, we'll be able to do things like normally off computing for IoT, be revolutionary to be able to do things like what I'm showing on the right in terms of state retention in flops, and then all kinds of other things with security, trim, reconfigurable computing. There's just a whole, we haven't had, in leading logic, we've never had a usable non-volatile memory. So we haven't really thought through a lot of this stuff yet. But the message here is it's probably a good time to start thinking about this, because when this SOT MRAM type stuff starts to really hit, there's going to be a ton of opportunity that we've just never had before to use a good non-volatile memory in logic. One of the holy grails is in machine learning land. When you're doing convolutions, you're dealing with a lot of data in convolutional neural networks. And you actually, just for your reference, you're talking about megabytes of data to deal with these various machine learning inference algorithms. And one of the holy grails is if we had a non-volatile resistor that we could tune, we could do multiply accumulates by storing the weights of these neural networks as resistance values, and then just through a current sum, real circuit design again, we can really condense the calculations from a digital perspective. And it sounds absurd because we all know how limited some of the resistors are that I just talked about, but you don't need a lot of bit accuracy to do good machine learning, turns out. So there's hope. And you will read, and I'll show you some papers here at CICC even, you're going to see a lot of papers that are really rosy about analog neuromorphic from a MAC perspective. And I want to, this is basically the same theme I gave you about DSA before. You have to look at the system level, right? You can do really good analog neuromorphic, the actual multiply accumulate, but you have to consider the broader picture, what's happening at the system level. First of all, does your customer, some customers care about energy and some care about area. You have to understand that. And we've done a lot of analysis of potential analog neuromorphic calculations. What we find is a huge variety of results. You can actually go backwards by a factor of 10 if you don't pay attention to what you're doing, or you can have a factor of 100 improvement just based on what the actual application is and considering all the dilution that happens when you actually look at a system level metric. And this is one really amusing example. So this is looking at the area involved in a 1T, 1R based MAC, analog MAC, where you see the area of the DAC and the ADC changing based on how we're configuring the size of the array. What you don't see that's actually in this graph is there's a little green bar at the top of all those. That's the resistor array, right? A compact resistor array is nothing, and everything is about how well you do ADC and DAC, which is probably good news for some of the people in this room, because if we're going this path, the value is going to be in how well you do DAC and ADC. And then a couple other warning comments about jumping into this space is you need to really understand what resistor you're going to use, PCM, MRAM, RRAM, what it can do. It needs to be very linear. If it's nonlinear, you're going to really cause problems with the neural network modeling. You have to be able to increment and decrement resistance. That's important to machine learning, and a lot of these memories don't let you do that. And of course, you have to meet speed and power goals. So there's really nothing out there that does it. You can't take anything on that slide of future non-volatile technologies and bank on it and say this is going to be easy and I'm going to go do this. You've got to do a lot of work. This is just a reference slide showing some of the digital and analog papers that I like to read up on. But the one example I wanted to talk about in this space is IBM's doing a ton of work in phase change memory in this area. But when you dig into what they're doing, there's a ton of overhead that they put in the higher level design to deal with the fact that phase change memory drifts over time. It's not linear and it can't decrement. So you can increment your resistance, and if you want to go backwards, you have to reset the device and then climb back up the curve. So there's a lot of stuff going on at a system level to get a usable machine learning analog neuromorphic. One last comment too is there is a holy grail in this space that we're going to be able to stack these resistors in 3D, given that we're going to have some good selector device, basically a diode, to allow us to go 3D. If this happens, then we're going to have a lot of different conversations, because we're going to talk about 4 or 8 times as much cache available on a chip than we have now, and that would be relatively important. But the other thing to pay attention to, why you should pay attention to this space is there's a lot of great progress in this area, and it's hypothetical that a selector is going to come out that's so good that we'll be able to use it in logic design to have programmable wires. So I would really pay attention to the selector space, because some of these things are looking good enough where we should be able to use them from a logic perspective to turn wires on and off. And that was a good reference paper. So in summary then, in More Than More, there are 2 big topics, both huge, huge upsides, not only at the system level, but for things to do that circuit designers can do to improve the systems. 3D IC, it's here, it's being driven. There's a wide variety of things you can do with it, 2.5D, 3D, the wafers, chip stacking. But you can bet on the fact that the interconnect density will get high enough that you'll be able to do things productively at the circuit level. And then NVM, I made a lot of fun, a lot of the technologies, but MRAM is a decent looking memory, and it's looking like it's got a roadmap to improve. It's not that expensive to put on a wafer. I think it's under 5% kind of tax to get it on a wafer. And there's a lot of great work in some of the other technologies. So they're coming, they're here, tons of opportunity in these 2 technologies. So that gets me to the last section, which is a lot of the things I've talked about are fairly short term. They're going to get us 1, 2 node kind of numbers. What can we possibly do looking forward? And everything we've done in the Moore's Law era, the whole 50 whatever years, has been CMOS. And for the most part, it's been confining the gate better, getting to the FinFET, and now we got the nanosheets coming, and we're stacking the transistors. So it's very simplistic in terms of technology advancement, which is making light of how hard it's been to get where we are. But going forward, we can see that that's really not going to get us much further, the CMOS paradigm. So going forward, there are things out there that are new materials and even new physics that are what we consider beyond CMOS that have a lot of hope. And I'm listing out some of my favorites. I'm going to talk about a couple of them. I'm going to quickly, and one other comment too, right? This is this can go hand in hand with the 3D technologies. So a lot of what stopped new materials in the past has been you need silicon CMOS still. We're going to still need basic silicon CMOS. And if you can't integrate it on a silicon wafer, it's a non-starter in a lot of cases. But with some of the low-cost packaging technologies, the wafer bonding for one, you might not be constrained by that. So you can start to think about, hey, maybe I'll put a weird 3.5 device on top of my CMOS silicon cost effectively with packaging technology, and I can do some really strange things. I'm going to quickly go through quantum because quantum is way off in the future. People ask me about it all the time. There's a lot of money going into it, but you're talking about 10 years before you do like real computing. There are some very specific examples that will come up in the next few years in the chemistry area because you can map qubits directly to electrons. But other than that, when you start digging into quantum, when they're talking about ECC, we talk about adding a couple of columns to a memory instance. They're talking about ECC where they need 1,000 bits of ECC for every physical bit. That's a quantum bit. So when they say I have a 100-bit quantum computer, what they mean is I've got 100 physical bits. Now I need 100,000 error correcting bits to make that actually work as a quantum computer. And that's not physically possible. When you look at how the systems are put together now, yes, you could buy a system. It's not really worth anything from a quantum computer. And then for the purposes of the printed version of the slides you're going to get, I'm going to cover that up, that disparaging comment with the fact that it's really impressive, the progress that's been made. And there's actually a talk here about that. What I will say is the quantum that's being done right now is very limited. There are a lot of other technologies in the hopper to pay attention to. Photonics, silicon-based stuff. The cryogenic transmon technology is what we can do now, and people are spending a lot of money on it, but pay attention to the underlying technology because something will probably come out from left field that'll jumpstart this whole plan. The other technologies I'm going to leave you mainly with a lot of reference material, but the two that are popping up a lot, one is superconducting logic. So when we benchmark transistors, a lot of times we look at energy delay plots, and you can change the VT of CMOS to go up and down the green line, basically. And if you don't have a transistor that is clearly an order or two magnitude better than CMOS, it's not worth having a conversation about. Because it's too much risk and trouble to do something different than CMOS. And there are some bubbles on here that are separated. And all of them say QF. So the one thing that does look good from an energy delay perspective is this quantum flux, which is cryogenic computing using, there's a lot of different kinds, but so that's some of the lingo. But you're using this Josephson junction idea. It's supercooled, superconducting niobium wires. We're using this superconducting tunneling effect that got a Nobel Prize. And the idea is that you actually it's quantized. So when you look at the theory and everything, you get a quantization of what happens. And an interesting trivia question that comes out of this is we all need to know what a volt is in our job, right? How do we know what a volt is? We actually now know what a volt is because of Josephson junctions. So the NBS, National Bureau of Standards, they do this 33,000 Josephson junction test structure that defines what a volt, that's the definition of volt for NBS now, using the fact that the quantum is those are all physical constants, right? So these quanta are you can get very accurate understanding of voltages and magnetic fields from Josephson junctions. Comparing quantum to CMOS, it's just changing from voltage to current, capacitors to inductors, and instead of states from 1 and 0, you get these little quantum fluxes that pop out, but they're only a few millivolts, and that's the beauty of it, right? It's very low power. And then the plot on the bottom is a 5-device flip-flop, so that's also really encouraging from a circuit design perspective. Now, I'm going to leave you just with a lot of reference if you want to read up about this, how it actually works. It's a lot of wording talking about how it works. A couple of the big runners in terms of emphasis. SFQ is the big one at the moment, but it's not simple. There's no fan out because of the superconducting wire issues. and then each gate has to be clocked. So it's very, very different than digital design. When you see papers that say I'm running 100 gigahertz superconducting logic, you've got to factor in, you've got to divide by the path depth in logic to get what the system would do, because everybody's got to be clocked. They're also not that scalable, so they're pretty big devices, and there's a lot of problems with the fact that that you still have losses in superconductors. So the summary of SFQ is the last big conference in the area. Northrop Grumman did try and make a CPU, and their paper didn't get to work. And then they had another paper with a smaller CPU, and they didn't get that to work either. So they're trying. They're at the point where they're trying to make CPU level stuff, but there's a lot of problems with how to design in superconducting. So I wouldn't bank on it at the moment. It is really attractive too, because it's just a wire. You can do everything in the wire. It's just capacitors, more or less. There is a big program at IARPA, and they're doing it the right way. They're funding a lot of design tools. But an interesting side is you could just take CMOS and make CMOS cryogenic. So we've all read in our textbooks about freeze out and what have you, but modern CMOS you can make work in cryogenic temperatures, and you can get somewhere between room temperature CMOS and superconducting cryo. So instead of 1000x or 100x, you might get 5-10x. But that's a big active area. And in fact, there was a really good paper at CICC from Google showing what they did in just cooling CMOS. So superconducting could be a big improvement to data centers at some point. It's pretty far off, and it's going to be a lot of tough design work. Spintronics is the other technology that gets a lot of press at the moment, and it is very attractive in the same sense. The big problem we have with CMOS is charging these nets up and down half a volt. That's where we get our problems with power and performance. And Spintronics can do stuff at a 10 millivolt level, right? So it's very attractive from that perspective. And it doesn't need a big refrigerator like superconducting per se. So it's very attractive in that sense. And also the fact that I'm going from a MOSFET to just a resistor. So it's very compact stuff that can be done in the wiring. This is basically MRAM. We're just using MRAM as a logic device. It's the same thing using spin current filtering. It can fit in the wiring, so you can do hybrid spintronics, CMOS hybrid stuff. That's really attractive. And then you can do really, really dense logic. So I'm showing you a truth table of a 3-input majority gate, and that's just 3 terminals, 3 vias, basically, in the wiring, right? And then you can do a 1-stack exclusive NOR gate on the right. So it's very attractive from that perspective, but these are just resistors, so they don't have gain. To actually make a real circuit, you got to marry them with some CMOS buffers, and that's where when you come out in the calculations in the WUSH, it's not as great as it looks just from an MTJ perspective. So the MTJs are really small, but you got to fit them into an inverter and deal with all the extra area, power, and delay of that. So there's hope that the devices will improve and we'll get beyond the CMOS line, but at the moment, nothing in the Spintronics land is looking like it's going to really supplant CMOS. Probably the one window that it might get to is something that's very slow but very power efficient. So there'll be certain aspects that we can use it for, but not for leading edge CMOS, probably. If you're interested in further reading, got lots of stuff for you here. Lots of great work going on. And then the last topic that I ran out of time for is, but it's also way out in the future, is photonics. And when I'm talking about photonics is there's a lot of interesting work, not just coupling lasers into the edge of a data center chip, but doing stuff integrated in the CMOS. So it's attractive in the sense that you can do, with photons, you can do things in terms of power and delay that you can't do with electrons. The problem is Moore's law has been so successful that the picture I'm showing you is not to scale. This is to scale, right? So that's the problem with photonics in the sense of doing meaningful information processing. But there's a really interesting topic, which I'll save for the talk I'm going to give in 6 years, because by then there'll be enough work on it. But if you're interested in reading up in some really science fiction stuff, the keywords plasmonics and metamaterials. it's a really interesting offshoot of the success we've had of Moore's Law, because what people have found is you can actually, using the ability to pattern nanometer features, layer-wise and feature-wise, you can actually convert this gigantic photon into what's called a surface plasmon that actually is really small, can propagate on nanometer wires, and then pop back out as a photon later once you're done with it. So it's really science fiction stuff. And so that's a field called plasmonics. There's a conference that's been doing plasmonics for 10 years. It's a lot of academic research, and it has a lot of promise, but it's still pretty far out from anything we want to use. But this is just one example of metamaterials. So the ability that we've made with the semiconductor industry is going to make some crazy new physics. There's negative diffraction materials. You could potentially, we've already sound cloaking with metamaterials, so you can already make devices invisible from radar or from a sound perspective, and they're talking about actually optical cloaks for, you can imagine people who build tanks are funding this. But there's some crazy physics coming our way, which we'll be able to utilize. Okay, so that was a lot of topics, and I struggled really hard. How can I summarize that whole set of stuff I just told you in one slide? And I'm going to try. So this is my summary of the technology roadmap. We have a standard Moore's Law. We're going to improve CMOS with $250 million EUV steppers. We're going to stack the transistors. There's a roadmap for potentially 20 years, potentially, with all the caveats I gave you. What we do see then, though, is very compelling uses of what we call more than more. The two big ones, 3D IC and novel non-volatile memories, in combination with using them in new architectures. So we've seen, for instance, TPUs, I mentioned analog neuromorphic. So those are going to be in combination, complementary to CMOS. There's not going to be a thing that replaces CMOS that's going to be the next, that's going to drive Moore's Law. We're going to have to deal with poor Moore's Law scaling and then augmenting it with these other more technologies. So things are going to get more complicated, not simpler. And then beyond CMOS, I talked about a few of the options. Some of them are going to come out. We just don't know when or how well they're going to work, but we're going to have to deal with splintering of this. And I actually didn't come up with this. I adapted this graphic from the report in IRDS, which is the follow-on to ITRS, the roadmap. The ITRS group went away. It's popped back up as IRDS, and there are some interesting reports you can get off the IRDS website. I modified their graphic to show you that basically the way we're going to make progress is less about Moore's Law and big processors, and more about integrating them heterogeneously, different technologies, different actual application logic in the 3D IC using the non-volatile memories, and then when possible using some of these fancier, more beyond CMOS devices. So what that means is it's good news for circuit designers, because it's not just we're shrinking transistors and doing the same thing and turning the crank. We've got to deal with very sophisticated design practices and getting good 3D IC design out, good memory uses of these new memories, and then all these new devices are going to require some very fancy circuit design as well. So it's actually the slowing, or at the end of Moore's Law, as I mentioned, is a big opportunity for us in design, because that's where the progress is going to come. It's not going to come from smaller transistors. So that's the end of my talk, and I want to mention that I did very little of the work I showed you. So these are the people that did a lot of the work. If the picture of the ice cream sandwich made you hungry, you can call David and complain. And as I mentioned, Mudit's done a lot of the work that I showed. He's going to be here in CICC, so you can talk to him more about it. He's going to be at session 25. And then I showed a lot of work I mentioned from Georgia Tech, Stanford, University of Michigan, and some of our other academic partners along the way. So hopefully it gives you some ideas of things you can do in the future, especially if you're a young person thinking about the choices between a career in hardware and software. I think there's a ton of opportunity in hardware, and hopefully I've given you some good ideas going forward. Thank you. I think we have a break,
Yeah, I have a break.
so I can be around for break questions as well.
Okay, I have one question. You mentioned the diminishing gain for the power and speed, power and performance. Can you give more insight on that? Why is the reason?
Well, the primary reason is that, in the old Dennard days, when we formulated Dennard scaling, you shrank the transistor and you got a lower gate capacitance. What you see at 5 nanometers is that the capacitance of the gate is a small minority of the total capacitance of the net. So you could cut that capacitance in half, and you're not going to get a big power and performance improvement. So you just, because of the parasitics involved, you just don't get benefit from the traditional Dennard scaling. That's the number one reason.
A couple of quick questions. You're mentioning lots and lots of rare earth materials and exotic things up there. What are the supply chains for those like? And is there any possible problem with unstable regions of the world?
Yes, yes. So there are lots of problems in that area. There are not just in logic materials, but battery materials. There are some problems with potentially some countries cornering markets. There's conflict issues. So a lot of companies, ARM being one, I know Intel is very public about this. You know, they've got to make sure they're conflict free if they're going to get their materials. And that was easy when you're talking about 10 materials. We're talking about the whole periodic table now. And there are some very limited places where you do get those. So that's going to be, and some of these things, the materials are so rare that it's questionable if we really start to use them in commercial CMOS if the supply is available. So great that we're making progress on some of this research, but we really do have to think through that question if we're going to put them into every single phone in the world.
I have a second dumb question. This is from a colleague who had done an analysis. I think there's some commercial MRAM that is available from some of the foundries.
Mm-hmm.
But you can buy from Amazon magnets that are powerful enough to erase it within the thickness of the cell phone.
Yep.
So you can wave magnets across your phone and erase the...
Yep. Yeah, so that is one reason why you might really want to look at some of the other memories for security purposes, or you have to deal with that. I mean, MRAM's going to be here. I mean, it definitely you can get it. It's a really interesting. It's a good memory, but yeah, from that perspective, that is a big cause for concern.
You didn't mention negative capacitance.
Yeah. It was on purpose. So it's unclear to me if negative capacitance FET is actually usable. From the sense of I haven't, and I admit I'm not 100% up to date on the reading the literature, but I haven't seen convincing arguments that the negative capacitance effect, which I believe is a ferroelectric effect, can operate at the switching speeds of an actual CMOS node. So it might be that it's very good for certain applications, maybe in memory where it's slower, but there's evidently a lot of papers that are coming out in this year that are looking at the frequency response of NCFET. I think VLSI's got a couple coming up in June. So we probably will know more this year, but for right now I just haven't seen a compelling write-up saying this is for real and it can be really used it can compete with CMOS at high frequency.
So I mean, right now when you have multi-core processors, a lot of the power is limited to how much heat you can actually extract.
Yep.
So with these, wafer stack.
Absolutely. Yeah.
Is that going to be an even bigger problem?
Absolutely. Yeah. So I didn't mention. So I gave you an example of Global Foundries where they took the memory out. Very simple. Just took the memory out and stacked it on top of the logic. What I didn't tell you is they put the world's largest heat sink on top of that thing. And then they went so that heat sink spread stuff out, and at the edge of the chip they had giant heat pipe TSVs all the way around the whole thing to get the heat back down to the package. And that was just the 2 layers memory over logic. If you're talking about 2 logic layers, 4 logic layers, absolutely it's going to be a big problem. There are really crazy things being discussed like microfluidic cooling to maybe get there. But what you really need is really good three-dimensional thermal analysis tools that don't exist yet to help you figure out that you're going to be good or bad. That wafer-to-wafer technology, by the way, that's actually very low thermal interface, right? It's just copper bonding. So that you can get heat between the layers. It's just what do you do with the fact that one layer is going to disturb the other one? And there have been attempts at 3D that were highly publicized in the industry that didn't come out as products, and thermal and or RF type noise problems are the issue. We really can't fully do system design yet with the tools we have. But yeah, that's the huge question.